Hello and welcome, ladies and gentlemen. We are in packet 2, we're in module 1, lesson 2, looking at activity 2.4 here. And we're just going to go ahead and jump right into it. So we're looking at this quadrilateral quad, which is over here. And you can see I've already done some constructions on it. I do this just to save time now. I realize that me talking a lot in combination with doing constructions just takes up a lot of time. So I'm going to go ahead and start doing this before most videos so that you guys can save yourself some time. I can save some time for you guys. So here we go. Construct the midpoint of each side of quadrilateral quad. You can see I have all of these arc markings. Okay, so this is something that's important. So I was telling you guys on the last test and for future tests, if you have markings like this on your paper, it shows me that you know how to find a mid segment or a midpoint on a line by constructing that perpendicular bisector. So if it does look kind of like a mess, and I could have erased it because I had all these markings in pencil and then I had these markings in pen, and it would have looked really sharp. But I wanted to leave these to tell you all that these are kind of what I'm looking for when you guys are doing your tests. In fact, they're exactly what I'm looking for when you're doing your tests, so just a heads up on that. So number 1, construct those. I did the constructions before, so that's good to go. 2 says, how many possible mid-segments are there for any quadrilateral? Okay, so we'll go ahead and look at this quadrilateral. And if you don't know what a mid-segment is, a mid-segment of a polygon is any line segment that connects two midpoints of the sides of the polygon. So here we have all of our midpoints. Okay. And so then a mid-segment, how many can we construct? So if I'm starting at this midpoint right here, I can go 1, and then across 2, and then down 3. So a common mistake that people would make is they'd say, okay, I have 1 midpoint, and I can draw 3 lines from that midpoint. So there's 4 midpoints, so 3 times 4 is 12. I can draw 12 mid-segments, and that's a common mistake, but it's actually not correct. So the thing you got to be careful of, okay, so I can go 1 here, 2 across, I'll do a little dotted line, and I don't even know if you can see that, but little dotted line there, okay? So 1, 2 across, 3 down. And then if I come up to this top one, I can do 1 to here, which has already been done. We've already counted for that one. I can go 1 across, and then I can go here, which is a new one. Okay, so we started from this right dot, we went up, across, down. We started from the top one, we went right, down, left, down, right. So now we're going to start on this right one. We can go up, that one's already been constructed. We can go across, that one's already been constructed. I can go down, this one has not been constructed, so that would be a new one. Okay, and then from this bottom one, if I went to the right, that's the one we just made. If I go across, we've already made that one, and if I go to the left, we already made that one from the first point coming down to here. So and then now all we have to do is count these lines. So there's 1, 2, 3, 4, 5 up and down, and then 6 across. So 6 would be our answer that they were looking for here. So you could make 12, but the thing is that there's going to be duplicates, right? So from here to here and from here to here is the same line segment, is the same mid segment, and we don't want to count that twice. So while your thinking wasn't totally off base in saying I could draw 3 from one of the midpoints, multiply that by 4 to get 12, you're not technically incorrect. You could draw 12 of them, but there would be 6 duplicates or 6 repeats, which means that there would only be 6 that are unique. Okay, so 6 would be our answer there. Number 3 says, draw the mid-segments that connect the midpoints of adjacent sides. What shape does it appear you drew using the mid-segments of quadrilateral quad? So I've already drawn those. These are the solid lines that we're looking at now. What shape does it appear that we have drawn? So some of you in class said square. Okay, and I can see why on this example you would think maybe it does look like a square. I think that they chose a poor example for this one because it does kind of look like a square. I think that what they should have done, because the answer they're looking for isn't a square, they're looking for parallelogram for this answer. Okay, so I'm going to go a little cross that out. Okay, so the answer they're looking for is parallelogram. So I think that they could have picked a better example to make it more obviously a parallelogram, because depending on your drawing, right, depending on your human error, this might have looked more or less like a square. So some of you, it probably looked exactly like a square, and you saying that isn't wrong, it's just that this was kind of a poor example. So the answer they're looking for there is a parallelogram. Okay, so now it says revisit the quadrilaterals you drew on patty paper in this lesson. Unfortunately, I've already recycled them, so I'm just going to go ahead and give a quick talk about this, okay? Because number 4 says draw the mid-segments connecting midpoints of adjacent sides for each of the quadrilaterals you drew on patty paper. Basically, do the exact same thing we did here, only for all of the constructions we did on patty paper. It says, make a conjecture about the figure created by connecting adjacent midpoints of a quadrilateral. So now we're making a conjecture about what shape is made by doing that. So we had one example, we said it's a parallelogram, and then they want you to do this with all of our prior constructions from this packet, and then decide what you think the shape is going to be every single time for every single quadrilateral when you do this. So instead of doing this with all of your patty paper, I would say do as many as it takes for you to see the pattern. Okay. So if it takes you one additional, so you did this example and then you do one of yours that you constructed, and then now you see the pattern, boom, awesome. Okay. You can be done there. If it takes you all 4, 5, 6, however many we did, that's totally fine as well. Okay, but the answer they're looking for here is that it forms, and it being this process. So about when we create, wow, I cannot read right now. Connecting midpoints of adjacent sides for a quadrilateral, we're saying that process, it forms a parallelogram. Okay, and so for some of the shapes, so say I have a rhombus right here. It's not the best rhombus, but we can pretend. Okay, say I have a rhombus and I connect all of these midpoints. When I connect the midpoints of adjacent sides on a rhombus, it makes a rectangle. Okay, but I can't say that that's true for every quadrilateral because, again, think back up to this example. This quadrilateral is a quadrilateral. It has 4 sides, and it doesn't make a rectangle on the inside. So my conjecture wouldn't be a good conjecture for me to say that every single time I make a rectangle, because on the one up here, on this one that was up there, right, that was not the case. But for a rhombus, it is. And for a square, if I construct all those mid segments and connect those, I get another square. Right? But again, it wouldn't be a good conjecture for me to say that all of them make squares, because when I do a rhombus, I get a rectangle, and when I do this quadrilateral up here, I get a parallelogram. So what do all of these things have in common? Well, they have 2 pairs of opposite sides that are parallel, which of course is the definition of a parallelogram. So that's what they're looking for here. So question 5 says, does your conjecture hold true for concave quadrilaterals? Use a drawing to justify your answer. So if you'll remember, a concave quadrilateral, okay, if you remember from the beginning of the packet, kind of looks like a boomerang, at least their example that they gave. There's lots of different examples of concave quadrilaterals, but I'm going to go ahead and go with this one. Okay, so they said, does your conjecture hold true for a concave? So what I'm doing here is I'm doing the same process, okay? Doing the same process, and now I'm going to connect all of these midpoints. I'm going to construct all these mid segments. Okay, and again, I'm freehanding this one. I could have constructed it before, but this one I hope we can see just with a freehand drawing, okay? So does your conjecture hold true? So our conjecture said that this process forms a parallelogram with any quadrilateral. So now it's asking, does it hold true for concave quadrilaterals? And again, my drawing is not perfect, but it looks to me like this. I could say that these 2 sides are definitely parallel. And these 2 sides, these ones on the left and right, while they might not look exactly parallel, they are pretty darn close. And because I freehanded this, I would go ahead and say that, yeah, this looks like a parallelogram to me. So does your conjecture hold true? I would say yes. And then for use a drawing to justify your answer, you could point to this drawing. Whatever drawing you make, that's all fine. If you wanted to put more words down here, if you wanted to elaborate more with words, you could definitely do that. But drawing this shows me that you know what you're talking about, okay? On to the next part, 2.4. Okay, again, I did all these constructions and measurements beforehand. So some of these, like part A, says draw any trapezoid with 1 pair of parallel sides, label the vertices. Well, I did that, TRAP, and then there's my trapezoid. You can see it. So that part's done. Part A is good. B says construct the mid-segments of your trapezoid. Construct the mid-segment of your trapezoid that connects the non-parallel sides. So they gave us this set of parallel lines, top and bottom. So my non-parallel sides would be my left and right side. So I constructed the mid-segment for those. You can see my arc marks. Okay, and you can see my little lines marking the midpoints, and I connected those with the mid-segment, so that's good, and then I labeled it A, B there. Okay, C says use a ruler to determine the length of each base and the length of the mid-segment, and I already did that as well. This is in inches. My ruler has a nice, so most rulers will break up inches into 16ths. Mine breaks it up into tenths, so you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it makes it easy for me to get these kind of hundredths approximations, right? Because 10th and then 100th. So it was, closer to 1.6 than it was 1.5, and it was past what I thought would be 1.55, so I went with 1.58 anyway. And then I did the same thing up here, 1.12. Anyway, so that was part C. D says determine the average of the lengths of the bases. What do you notice? So my base lengths, remember the bases of a trapezoid are the 2 sides that are parallel, and since they provided these parallel lines for us, I know that those are going to go ahead, my top side and bottom side are going to be my bases. So I can add 1.12 with 1.58 to get 2.7, right? And then, so I want to take the average of those. So since I added up 2 numbers, I would divide 2.7 2.7 divided by 2 is 1.35. Okay, so now here's my number that I got for my average of the two, 1.35, and it asks me what I notice about that number. Well, it looks to me like this number matches the length of my mid-segment that I just constructed. So that would be something that's good to notice there. So I'd say, so average of two bases equals length of mid-segment. And I'm sorry, I kind of squished this on here. Doing my math like this was helpful to show at first, but then I kind of ran out of room to write. So yeah, average of the two bases equals the length of the mid-segment. So that's what I noticed, right? And now E says, compare your answers to part D with those of your classmates. Make a conjecture about the mid-segment of a trapezoid that connects non-parallel sides. So unfortunately, I don't have any classmates here. I do have some housemates that are kind of lurking around the house. I hear one of them making breakfast right now. But they unfortunately didn't do their homework. They didn't do this. So I can't compare with them. So I'm going to go ahead and make a conjecture on my own, okay? And so a good way to approach making conjectures, especially in these packets, they like to set you up for success, right? So they said, what do you notice? Well, you notice that the average of the two bases of this trapezoid equaled the length of the mid-segment. So what's a conjecture? What's an assumption that I can make for all trapezoids? Well, since I just noticed this with one trapezoid, I could maybe assume that, that the average length of the two bases of any trapezoid is equal to the length of the mid-segment. And if you wanted to get really specific, the mid-segment that connects non-parallel sides. All right, because we're making a conjecture about the mid-segment of the trapezoid that connects non-parallel sides, so you could get that specific here. If you said the mid-segment, I would know what you were talking about, but if someone were to walk in and look at this conjecture on its own without the context of this paper up here, they wouldn't know what mid-segment you were talking about, so you would want to be more specific. But in the context of this packet, if you just said the mid-segment, I would know what you're talking about. Okay, but someday when you're a mathematician and you're publishing your work and everyone needs to know exactly what you're talking about, you would want to be more specific like this. So yeah, there you go. That was 2.4, not too bad. Pretty short video. Hope you all have a wonderful day, a wonderful weekend, and I will talk to you soon. See you in class. Adios.